Hey everybody, I'm really excited about today's video because we'll be testing a traditional generator, an inverter generator, and a power station to answer three simple questions. Question number one, how clean is the power output from each one of these options? Question number two, which one is the safest for electronics? And question number three, which one handles real-world loads the best? Now, I think I should clarify up front, this is not a sales video. I'm not here to tell you which one you should buy. I just want to do some basic testing to hopefully get rid of some rumors and some questions that people have about the power output on each one of these options. So over here on the side of my house, I've put together a basic testing setup looking at the equipment we'll be using in the video. I have my oscilloscope. I have an amp probe meter to measure the total harmonic distortion. We'll also be seeing how loud each option is. And then I have this line EMI meter that we can measure the electromagnetic interference. Now we will be doing surge capacity testing using this table saw, and then also I have two of these 1500 watt heaters to run a max continuous load test. So my plan for the testing is to have the power station and generators out in the grass. I have this 25-foot 10 gauge extension cable that will be connected up to each one, so the results should be the same for each one of the tests. So to kick off our testing, we're going to start with the traditional generator or non-inverter generator. This is from Troy-Bilt. This is rated for 3,250 watts continuous output. Now, I've heard that these generators put out dirty power, so I'm kind of curious what type of power output we get from these. I know one of the downsides is that the engine is directly connected up to the generator output, and so if the engine RPM drops, so does your voltage and your hertz output. So this will be interesting. So I've just started up the generator. It's about 25 feet away, so let's see how loud it is. So the generator's been running for about 5 minutes now. It's warmed up, so I've connected in the oscilloscope. And take a look at this wave output. It's kind of like a sine wave, but we got some really big peaks at the top and bottom. Now, if you look at the voltage, it's jumping around a bit, so 117 all the way up to 122 volts. And the frequency is a bit high. We should be right around 60, but we're seeing about 61 to 62 hertz output. Pretty interesting. I'm curious what will happen to the sine wave as we connect up a load. In the next test, I've connected up my amp probe meter to measure the total harmonic distortion. Typically, you want to see under 3%, and we are sitting at about 5.8%, so quite a bit off of what you'd like to see from the power output. For the next test, I've connected up two 1500 watt heaters. They are running at max output, so we are pulling about 3,000 watts from the generator. Let's go ahead and take a look at what the sine wave is doing now. So with the generator running that 3,000 watt load, I've connected up the oscilloscope again, and take a look at the sine wave. It is quite changed from before. So if we look at the voltage bottom left, we're showing right around 104 volts. The frequency is about 57 to 58. I am seeing a little bit around 59 hertz, but I'd say that that sine wave output is just not acceptable for any sensitive equipment that you'd ever want to connect up to this thing. With the generator under that 3,000 watt load, I'm measuring the total harmonic distortion again, and we are seeing 7.7 to 7.8%. It is jumping around a little bit, but that is really bad. So I've just disconnected the two heaters, and now I want to test this table saw. So let's see if this generator can handle a large surge load. So let's go ahead and turn it on in 3, 2, 1. So it did power up the table saw. I did hear a bit of voltage drop. Let's go ahead and try it again, but we'll look at the oscilloscope this time as we do it. Okay, so here's the table saw a second time, but we are watching the waveform output. Let's see what happens. 3, 2, 1. In my final test on the traditional generator, I've connected in my line EMI monitor. This measures the electromagnetic interference that the generator is putting out. It's right around 515 millivolts, so not too bad compared to power stations I've tested in the past. Well, now that we've finished testing the traditional generator, let's move forward with testing the inverter generator. This is from Pulsar. This is the GX400BN. I've owned this for a couple years now. Now this one's actually rated for the same power output, 3,200 watts continuous. This is a dual fuel option, so it runs on both gasoline and propane. I'll be testing with gasoline. Let's go ahead and get it started up and see how it differs. I just started up the inverter generator, and I can already tell that it's much more quiet than the traditional generator. At 25 feet away, let's see how loud it is. So I've connected my oscilloscope up to the inverter generator with no load. And take a look at this sine wave output. It's a very clean, pure sine wave output. If we look at the voltage at the bottom left, we're showing 125 volts. The frequency is right at 60 hertz. It's 59.9 hertz. So this is very good compared to the previous generator. So moving on to testing the total harmonic distortion, we are seeing 0.5%. So very good on this inverter generator. Moving on to the next test, I've connected both the heaters up to the inverter generator. So let's see what the sine wave output looks like now. So zooming in on the oscilloscope, you can see the sine wave output is pretty much the same. It's still very good. Voltage, we're showing 121 volts, 60 hertz. Everything looks basically the same as it did when it was under idle. So very impressive output on the inverter generator. Measuring the total harmonic distortion while under full load, it's still under 1%, showing 0.7%. So I've disconnected the heaters. Now I want to test the table saw. So we'll see how well the inverter generator can handle a surge load like this. So 15 amp table saw in 3, 2, 1. It looks to power up the table saw just fine. Let's go ahead and do it again, watching the oscilloscope. Moving forward with the second table saw test. 3, 2, 1. So after seeing both the inverter generator and the traditional generator try to start up the table saw, the inverter generator definitely did better on that. Measuring the line EMI, or electromagnetic interference, the inverter generator has, it is a bit higher than what we saw on the traditional generator at 1500 millivolts. So up to this point in the video, we've tested both the traditional generator and the inverter generator, and boy, did we tell a difference in the power output from those two models. Now what I want to do is test this power station here to see how it compares against those two. Now some people like to call these solar generators. I absolutely hate that term. I call them power stations because they're basically a battery with an inverter, and they have the ability to charge with multiple inputs, not just solar. So later in the video, I'm going to talk about the benefit of having both a power station and a gas generator in your setup. But the reason I chose this one is because this one is similar to these two here in size. This is the Anker Solix F3000. It performed really well in my testing. This has a 3 kilowatt hour battery and a 3600 watt pure sine inverter. So I have the power station plugged in and turned on. It's 25 feet away, so let's measure how loud it is. Now obviously this is kind of a joke because power stations don't make much noise. That's one of the biggest benefits, is you don't have this large engine running in the background. So my oscilloscope is connected to the inverter output. We are showing a pure sine wave output. It's at 121 volts and 60 hertz. You can see it's between 59.9 and 60.2 hertz. And this is what you'd expect from a modern power station. You get a very clean sine wave output. Measuring the total harmonic distortion on the power station, we are seeing 1.2%, so just a little bit higher than the inverter generator, but well within tolerances. You just want it under 3%. Moving on to the next test, I've connected both of these heaters up to the power station inverter, so let's check out the sine wave. So if we zoom in on my oscilloscope while the inverter is running the load, it's still a very good pure sine wave output. We're showing 119 to 120 volts at 60 hertz. Now I wanted to measure the total harmonic distortion again under max load, and we are showing 1.2%, so it's actually the same as before. Moving on to the next test, I've disconnected the heaters. Now I want to see how it handles a surge load, so turning on the table saw in 3, 2, 1. So it powered up the table saw just fine. Let's go ahead and take a closer look at the oscilloscope and power it up a second time. Powering up the table saw a second time in 3, 2, 1. And finally, let's go ahead and test the line EMI, or electromagnetic interference, on the power station. You can see it's right around 1990, just a little bit higher than what we saw on the inverter generator. Wow guys, those were some really surprising results. I have never connected up an oscilloscope to a traditional generator or an inverter generator. I've only tested power stations, so I had a few surprises. First off, the power coming from a traditional generator was quite bad. The total harmonic distortion was really bad. The voltage in hertz was kind of just all over the place. So if you're going to be connecting up sensitive electronics, I would not recommend powering them with a traditional generator. Now, I was also surprised with the quality of the power that I got from the inverter generator. It actually had better output than the power station I was testing, which was pretty impressive. I was not expecting that at all. Now, when it comes to sensitive devices, people might be wondering, well, what are those sensitive devices? What can run off a traditional generator and what can't? Well, let's go through some of those items. So starting with items that are generally safe, these are incandescent light bulbs, space heaters with no circuit boards in them, toasters, hot plates, electric kettles, basic coffee makers that are not smart, brushed power tools, and simple AC fans. The next category of items are generally okay. They're safe, but you do want to use caution here. This is any device that has an external power supply. If the power supply gets extremely hot, you're going to want to stop using that device on the generator. So this list includes phone and laptop chargers, TVs and monitors, desktop computers with a quality power supply, gaming consoles, routers and modems, LED lights, small electronics with power bricks. Now, like I said earlier, if the power supply gets really hot, you're going to want to not use it. And also, if the device is really expensive and you don't want to risk it, then I wouldn't recommend connecting it up to a traditional generator. And finally, items that I would not recommend connecting up to a traditional generator include audio or studio equipment, medical devices, inverter-driven appliances, modern refrigerators that have some sort of circuit board in them, variable speed HVAC systems with brushless motors, mini splits, inverter washing machines, microwaves, and pretty much anything that you would not trust connecting up to dirty power. Now, going back to the 3 questions that we asked ourselves at the beginning of the video. Number 1, how clean is the power from each source? Well, now we know that a traditional generator puts out pretty dirty power, and I'd recommend using a different option. The power coming from an inverter generator is very good, and it's basically the same as a power station. Question number 2, which is the safest for electronics? Well, that's going to be an inverter generator or a power station. And which one handles real-world loads the best? Well, both the inverter generator and the power station did pretty good on the surge capacity and continuous loads. The power station did do a little bit better on that surge load. Instead of getting, a really messed up sine wave, we just saw some distortion on the top and bottom, where with the inverter generator, we saw kind of the sine wave get interrupted a bit more. Now guys, I learned a lot from the testing in the video today. I had no idea there'd be such a difference in power output from different types of generators. So if anybody is ever going to ask me what type of generator to buy in the future, I'm definitely going to recommend an inverter generator. Now, when it comes to power stations and generators, they go hand in hand. And I recommend owning both of them because my priority is to use my power stations to charge with solar because it's completely silent and the sun is unlimited power as long as it's shining. But if you happen to have a storm or it's at night and you need to charge your batteries, you're going to want to use a different charging source like a generator. But trust me, you do not want to be using a traditional generator to charge your power station. Now, I recently had an influx of questions about using a generator to charge a power station. A lot of people were wondering, hey, if I charge my power station with the generator, is it going to kill my devices? And the answer is no. As long as you're using a high quality inverter generator, the power is actually really good. Now, I'm sure there are a bunch of videos that I could do. If you have any other questions or any video ideas that kind of go along with this topic, make sure you leave a comment down below. Guys, thank you so much for checking out the video and supporting the channel. If you guys like this type of testing like I do, make sure you check out my other videos. I'll recommend a couple of other ones that you can check out on the screen. Until next time, we'll see you guys later.